M is the direct sum of M1 and M2 if and only if their two conditions are satisfied. The first one is M is equal to M1 plus M2. Second, M1 intersection M2 is equal to 0. Now the proof. Let us suppose that M is a direct sum of M1 and M2. Then by the definition of direct sum, every element of M can be uniquely expressed as the sum of one element of M1 and one element of M2. Then M is equal to M1 plus M2. Let 0 is not equal to small m and M1 intersection N2. Then small m belongs to M1 and small m belongs to M2. Obviously small m belongs to capital M. Capital M is a direct sum, so small m is equal to capital M plus 0. Small m belongs to capital M1 and small m is equal to capital M, is that small m belongs to M2. Now small m is equal to 0 plus m and capital M belongs to M2. In this way, small m can be written as in two ways, which is not true, and so small m is equal to 0. Now M1 intersection M2 is equal to 0. Conversely, suppose that uh, capital M is equal to M1 plus M2 and M1 intersection M2 is equal to 0. Then we have to prove that capital M is the direct sum. But equation first, this one, every element of M can be expressed as the sum of one element of M1 and one element of M2 for uniqueness. Let small m is equal to M1 plus M2 and M is equal to M1 dash plus M2 dash. Thus M1 plus M2 is equal to M1 dash plus M2 dash. So it can be written as and M1 minus M1 dash is equal to M2 dash minus M2. Equation number A. Uh, since M1 and M2 are submodule, and so M1 minus M1 dash belongs to M1 and M2 minus M2 dash belongs to M2. But by equation number A, M1 minus M1 dash belongs to M2 also, and so M1 minus M1 dash belongs to M1 intersection M2 is equal to 0. And M1 minus M1 dash is equal to 0, which implies that M1 is equal to M1 dash. Similarly, M2 is equal to